How's it going, everyone? Mr. Geyser here with the Lesson 9B video, still on our inverse trigonometric functions. For this lesson here, if a function is a one-to-one, meaning that it passes that horizontal line test, then its inverse relation is also a function. This is for sine, cosine, and tangent. We have restricted the domains for each function to discover these properties. Remember our inverse lesson from Unit 2, where we observed that when we solve out this inverse function and we plug it into our function, we're still going to get back out that original input. And it doesn't matter if we plug our function into our inverse function, we're still going to get back out that same input. Doesn't matter the order in which we plug in the function or inverse function, as long as we're plugging them in together, our input should then equal our output. We can apply these properties to our sine, cosine, and our tangents and their inverse functions for these following properties. We do want to try and restrict our x values for all of these kind of composite functions, and I want you to observe that when we plug in the inverse sine or the inverse cosine of their corresponding trig functions, we're still going to have that same input domain restriction of -1 to 1, where our x can be plugged in as -1 between 1. However, if we flip that around, where we're plugging in sine or cosine into their corresponding inverse trig functions, these domains were actually the ranges of these previous two examples. So when we're plugging in these sine or cosines into their inverse functions, for sine we get that -pi/2, pi/2 for the x values that we can plug in. And for cosine, we can plug in anything between 0 and pi. Now for tangent functions, we have no restrictions when it comes to plugging in values into the inverse tangent. And remember, that inverse tangent function was that sideways graph that went on to -infinity and positive infinity. It's only tangent that has a restriction between both of those vertical asymptotes. For that parent function, those two vertical asymptotes occur at that -pi/2 and that positive pi/2. The restrictions on x for inverse properties are a little tricky. Let's consider some examples where you need to find a reference angle. For example 8, we want to find the exact values, if possible, of these following three examples. For part A, we want to try and find inverse sine of 2π/3. Well, really, I need to solve this interior argument first, and since I know I'm dealing with these radian values, let's just bring back our unit circle. Now with our unit circle, it's so easy to find when sine is equal to 2π/3. Well, I just find 2π/3 right here, and I know sine of 2π/3 is that y value of √3/2. Now with that knowledge, I'm able to plug in that √3/2 into that inverse sine function, because these two things are equivalent. That step 2 is that inverse sine of √3/2. We're going to set that equal to our theta, and then for that step 3, we're just going to make this equal to sine of theta is equal to √3/2. And now we just need to look at the y values around our unit circle and see when sine of theta equals √3/2, and we find that it's still that same point. So this is a good sign. Our inputs are actually our outputs. But notice that for this y value, √3/2, this position of 2π/3 is not in the domain of this inverse sine graph. Since we're dealing with this inverse sine, we just want to look at that domain of -π/2 to positive pi/2, where the y value is still equal to √3/2. And we can spot that at pi/3, our y value is still equal to √3/2. So that there becomes our answer, as theta is equal to pi/3. Now for part B, let's try and solve out a cosine example. Well, for cosine, we're still going to follow those same steps. For that first one, we want to try and solve in that interior section for our inverse cosine. For that inverse cosine of 3π/4, we're just trying to find when that is equal to theta. We're able to rewrite this as that restriction, where we can say that cosine of theta is equal to 3π/4. Easy. We just want to find when the x value, this value here, is equal to 3π/4. And, it never is nowhere is the x value equal to 3 pi over 4. Remember, if you have a cosine of theta or a sine of theta, you're trying to find when on the unit circle the x value for cosine, the y value for sine is equivalent to that cosine of theta, where this cosine of theta would then be equivalent to that radian. In this case here, this is outside of that defined domain. That x never equals 3 pi over 4. This does not lie in between -1 and +1. Now, let's take a look at part C, where hopefully we will actually get a real answer. For part C, we still want to try and find that interior argument for part C first. We want to try and locate when cosine is equal to our 7 pi over 6. So I look for 7 pi over 6, happens right down here. And now I want to grab the x value at that coordinate point. That x value happens to be that negative √3 over 2. So I set this equation equal to √3 over 2. I now want to plug in that √3 over 2 back into that original inverse function. And we now want to try and find inverse cosine of √3 over 2, where we know that that's equal to theta. And for that third step, we're just rewriting it as a cosine function. We know for that cosine function, we're going to still be restricted by that domain between 0 and pi because we're still inside this inverse function. It's just rewritten as this cosine function. And I want to try and locate when my x value is equal to -3 over 2. And my cosine theta is equal to -3 over 2 at exactly 5 pi over 6. Now, for example 9, we want to try and evaluate these composite trigonometric functions that might not fall on exactly any of those radians for that unit circle. For example 9, we want to try and find cosine of inverse sine of -1/2. Now, this does happen to fall in our unit circle, but I want to show you how you don't need the unit circle to solve these out. Really, all of this inverse sine of 1/2 is just some theta value. And we also know that sine, this here, can be rewritten as sine of theta is equal to that -1 over 2. But notice that sine of theta really is just this ratio of the vertical displacement divided by the hypotenuse. Well, if I have that vertical displacement and a hypotenuse, I'm able to graph it as this triangle, where I know that that terminal ray is equivalent to 2, that vertical displacement is -1, and this horizontal displacement would just be my x value. Now I want to try and find what that x value is, and in general I'm going to use good old Pythagoras, that a squared plus b squared equals c squared. In our case, x squared plus y squared equals h squared. My first step is just to subtract that y squared to both sides, try and get x squared by itself. I'm just going to square root x to both sides, and now I have a known equation to solve for x. But notice this shortcut. Kind of like that b and p relationship that we have, if we just switch out y and x in these problems here, we just find the other side. So if we're ever given the hypotenuse in one of the sides, we can use one of these equations to find the other. In our case, we're going to use that top equation there, where we're plugging in 2 for hypotenuse, 1 for our vertical displacement. We find that it's going to be 4 minus 1, or really the square root of 3. Now, we know that this sine of theta is equal to that -1 over 2 with this ratio. And really, all we're trying to find with this original problem is what this cosine of theta equals. Because that inverse function is just equal to some theta amount. We don't really care what that theta is. We just care what that cosine of theta is equivalent to. And we know that this cosine of theta is equivalent to this triangle that we made. And the ratio for cosine of theta is just the horizontal displacement divided by the hypotenuse. And we already know that horizontal displacement is going to be square root 3 divided by 2. So our final answer to our problem of cosine of inverse sine of -1/2 is equal to √3 over 2. It's almost like we skipped past trying to find the exact theta amount, and we were able to derive this answer simply based on that ratio of cosine and sine. Let's try that one more time with example 10. We want to try and find the exact value of sine inverse cosine of this 5 over 13. Now 5 over 13 is not inside of our unit circle, so this is going to be a brand new kind of function. I do want to try and double check that this 5 over 13 is inside that domain for inverse sine, which it is. It's still within that -1 to 1 range. So I'm good just to try and solve out that inverse cosine of 5 over 13 equals theta. Well, I'm able just to rewrite that as sine, or cosine of theta is really equal to that ratio of 5 over 13, where that horizontal displacement is just going to be equal to 5, and that hypotenuse is just equal to 13. And now, luckily for us, we can use that equation we found in that previous example to solve for y. In this case, we're plugging in 13 minus 5 here, where 13 squared minus 5 is 169 minus 25. This here is 144. Square root 144, 12. Easy as cake. Once we're able to find what y is here, we're just trying to find whatever that sine of theta is equal to. I have no idea what that theta is, this theta here. But I know whatever that theta is going to be, it's going to be that ratio of this vertical displacement divided by this hypotenuse. So I can just write 12 over 13, where my answer for problem number 10 here is just sine of inverse cosine of 5 over 13 is equal to 12 over 13. Now, for our final two examples of this lesson here, we're taking a look at example 11 and example 12. In example 11, we're trying to find if x is between 0 and 1, we want to write sine of inverse cosine of x as a general algebraic expression in terms of x. What example 11 is trying to have us find is if we try and take cosine, or inverse cosine of x, we know that's going to be equal to some theta. We then want to try and find when what sine of that theta is equal to. Well, notice that this final ratio here is always going to be that vertical displacement divided by that hypotenuse of that original inverse cosine or cosine graph that we created. So it's defined within that range and domain of our original argument of this problem. What we want to try and show is that this x down here is always going to be some x. This h up here is always just going to be some h. And this y here is always equivalent to that square root of h squared minus x squared. So whenever we have a sine of inverse cosine of x, we really are just trying to find this ratio here of the root of h squared minus x squared divided by our hypotenuse squared. That there is exactly equivalent to our inverse cosine of x of sine. And if we're a bit clever, we can actually find that general form not just for inverse cosine to sine, but inverse sine into cosine, where we're just changing the x here for that y value. Now remember, these two expressions are only valid to that very, very slim domain between not including 0, but really close to 0, and including 1. These are the only time where these two equations are valid, but they are useful to have in your back pocket. Now, for example 12 here, an airplane flies at an amplitude of 5 miles towards a point directly over your house. In part A, we want to write theta as a function of x. Notice for us here, we're not going to use a cosine or sine function. Rather, we have this x value and this y value given to us. We don't know what x is, but we have our y value here. Since we're only given one of the two sides, we can't find the full triangle. But as long as we have this tangent function in our back pocket, we can find that it's just going to be this vertical displacement over that horizontal displacement. So really, it's just going to be 5 divided by whatever x is. In terms of theta, theta is going to equal the inverse of tangent of 5 over x. For part A, we wanted to try and find an equation just for theta. Since we're only given this y value here, and we want to write it in terms of x, we need to use this inverse tangent function. In part B, we want to write theta when x is actually 8 miles. What we're going to do is we're just going to plug in inverse tangent of 5 over 8. And for me, I don't happen to know that off the top of my head, so I'm going to use that handy dandy TI-84 calculator. I'm going to quit here, And now I'm going to use that second tangent function here, and all we're going to plug in is that 5 divided by 8. And I know that for that plane is going to be exactly 0.558. That radian is equal to 0.5586 radians. For this here, we can find that it's actually 32 degrees by multiplying it by that 180 degrees divided by pi. For this here, thank you very, very much for joining me on this 9B lesson where we took a look at a few applications and the composite functions of our inverse and our traditional cosine, sine, and tangents. If you have any questions, please leave them in that comment down below, and I look forward to seeing you guys in class. Take care.